we studied about design of machine components subjected to fatigue loading with non-zero mean stress, that is sigma m not equals to 0. So this is the case we were solving it. In this case we have seen that generally we have sigma amplitude, sigma mean. When the sigma mean full reversal, we know it is equals to SE, but the failure points were all over. So what we did was we have come up with a Soderberg line, then a modified Goodman line, and this is the yield line, and there is something called as a parabolic curve, which is Gerber curve or Gerber line. And we have written down the equations for this, the failure envelope for different cases as following. The Soderberg line would be Sm by Syt plus Sa divided by Se is equals to 1, and it is Sm by Sut plus Sa by Se is equals to 1. We know that where Sm is equals to factor of safety times sigma mean, and Sa is equals to factor of safety times sigma A. In the Gerber line or Gerber curve, we have shown that it would be quadratic, so whole square in the Sm, and is the Gerber curve. And then these are the kind of things which we generally follow for the when the fluctuating stresses are there. Then we have also corrected the Goodman curve further, because at higher mean stresses only yielding would take place, and hence we have proposed a modified Goodman line as So up to one point, if you look at AB is a Goodman line, and DC is uh, is the yield line. At higher values of the mean value is given by the yield. That's the reason the yield locus for the augmented or the modified Goodman would be A, B, and C. So depending upon the ratio of sigma A by sigma M, which will give us theta, right? So if you are having a ratio of sigma A by sigma M which is not equals to 45 degrees, then you will see that it falls under AB. If it falls under this one, right, then you have it is 45 degrees. So we need to make sure that when we are designing up to AB, we have 1 point, and BC, it is the yield line that governs the things. Based on these things, we have also solved a couple of examples in the previous class, and then we also gave, if you have multi-axial or a triaxial loading, then we have given you something called as von Mises criteria. Under combined loading. So for 2D, we have showed that based on the von Mises criteria, we can write our effective sigma A dash is equals to sigma XA whole square minus sigma XA sigma YA plus sigma square YA plus 3 times of XY amplitude under root. Similarly, for a mean value, which is sigma X mean value whole square minus sigma X mean sigma Y mean plus sigma Y mean whole square plus 3 tau square XY mean value is the effective for the mean. And then once you know sigma A and sigma M dash, then you will apply one of the above criteria for non-zero mean stress to designing the things. So if somebody asks for augmented or a modified Goodman thing, you would use ABC curve. Otherwise, you would only use, if it is Goodman curve, we will use this Soderberg criteria. This would be there, and Gerber thing is this. However, you can see that Gerber is much more closer to the failure points. The dot points are the failure points. Okay, so this will complete the design of fluctuating loads under non-zero mean, and today we start on welded joints. It's a new chapter. So we will initially go through a couple of definitions and types of welded joints and strength of the welded joints, and then we design based on the strength of the welded joint, we'll design different structure without application of pressure. This is the definition of welding. Next, and why welding is preferred? Because welding method for obtaining a permanent joint in metallic materials. Now, there are two distinct applications of welding. Two distinct applications welding, and those are, the first one welded joint as a substitute to riveted or bolted joint, and the other application is a welded structure as an alternate to casting or forging. Now we will see the advantages of welds of welded joints over others. Typically, riveted joints require additional material like cover plates, gusset plates, clip angles, straps, and a large number of rivets, which increase the weight of the component. While a welded is lightweight due to no additional or addition of parts. There may be some small amount of filler materials, but that is very insignificant, and hence you can say that this is lightweight compared to the riveted structures. Secondly, welded steel structures are lighter than the corresponding iron casting by 50% and steel casting by 30%. So because of this, you will reduce a lot of dead weight, and that will also help you in the design. The third one is the cost of welded assembly is lower than riveted joint. Further, design of welded assemblies are easy, and they are economical and can be modified easily changing product requirements. When you become a design engineer, generally the customer would keep on giving his criteria, which sometimes as the product gets designed, there are several changes in the product specifications are made. And in such cases, if you are relying on the welded things, what would happen is you would have already driven the holes, riveted holes, and that will make those sections critical sections, and you cannot even change those things. If you change again, it will again require a patch or a repair or something like that. Whereas with welded, you can easily get over with the changes because you can change it from one place to other place. That's a good thing about it. Further, welded assemblies are tight and leak proof, which are required in certain applications as compared to riveted assemblies. Further, the production time is very less for welded assemblies. In riveted joints, holes driven that leads to reduce in the net cross section which in turn results in stress concentrations such problems are absent in welded connections because you are not driving any holes. Because we have seen that wherever we had a stress concentration, there we will have to include for several factors like knot sensitivity factor or stress concentration factor, and that will kind of make our design bulkier. The welded structures has smooth and pleasant appearances. Compared to riveted joints. And strength of the weld or the weld joint is generally kept higher than the joining plates. Finally, if you have complex shapes like machine components, of complex shapes such as circular steel pipes, for example, find difficulty in riveting. However, they can be easily welded. These are the general advantages you have when you're thinking about the application related to the joints. Similarly, there are also certain applications advantages when you apply it for the structure as an alternate to the casting or forging process. So, advantages of welded structure over cast iron structures. Generally, welded mild steel plates, angles, and rods are much lighter than the casted or cast steel. Secondly, casting requires to maintain uniform and minimum section thickness, whereas in welded structures, the designer has more flexibility to use thick plates only at places where high strength is required. So I will tell you this as a one good example. Generally, when you look at the very big steel bridges in railways, they don't use rolled structures or casted ones because you have to maintain a uniform thickness and minimum thickness for all the cross sections. Whereas if you use plate cutter with the welded things, you can save a lot of self weight and the material from it. Thirdly, welded assemblies are more easily machinable than castings. Further, if somebody wants to start a weld shop, the capital investment of welded or welding is considerably lower than that of a foundry shop. There you need to invest for heavy hammers, and not only hammer, you need that much amount of in order to forge, you need to have a lot of load cells to engage with the amount of energy that is required to plastically deform the materials. Then so these are the preliminary advantages of it. There are also certain disadvantages. Of welded structures. So those disadvantages would be: first, they are very poor in vibration. So vibration damping is poor in welded structures as compared to further, the thermal distortion from welding induces residual stresses. Hence, additional process such as stress relieving heat treatment is required to relieve in welded structures. This is the most important problem because of the thermal distortion. The residual stresses will also affect the longevity of the structure. Next, the quality and the strength of the weld joint depends upon the skill of the welder, especially for large structures. It is difficult to control the quality due to high volume and several welders are involved. Since this is a specialized thing, you need a trained kind of a person to weld the things. Further, if it is a large structure, since each welder would weld in a different manner, his quality would change from person to person. When you are really dealing with a large volume or huge volume, then the maintaining quality, overall quality, would be little bit tiresome, because it would depend upon the least skilled or the person who does the weld in a not a proper manner. So that subjectivity is always there with respect to this welded structures. Further, the another important disadvantage is the inspection of the welded joint is more specialized and costly compared with the inspection of riveted or casted structures. Since from outside doesn't tell you anything, you need a kind of X-ray diffraction techniques to inspect the kind of quality of the weld, whereas for the riveted or other things, a manual inspection is sufficient. So not only the skilled labor, but also to do the quality check, it would be costly. And the execution is easier, but quality check is the costlier part in the welded things. Further, the process of welding, we'll talk about the welding process. And they can be classified into two groups. Here the first one is welding process. Heat alone to join two parts, as we discussed in the definition of welding. The other one is welding process that use combination of the heat and pressure to join the two parts. So these are the two things, and this process which we are seeing, the first one, is also known as fusion welding process. So let us understand what is fusion welding process. In this method, the parts to be joined are held in position and molten metal using the parent or filler. Filler means an external filler. Is supplied to the joint. Joining surfaces of the two parts become either plastic or molten under heat, and after cooling fuses or solidifies the two parts into a single unit. So this is what is called as fusion welding process. Further, this fusion welding is further divided into three categories. One is thermit welding, gas welding, and electric arc welding. So in the thermit welding, in this method of welding, a mold is placed around the joint contains a thermit and a reservoir of finely divided iron oxide aluminum. When ignited, thermit starts the chemical reaction and converts the iron oxide into molten steel. This molten steel melts the two parts and forms joint on solidifying. The advantages of these are all parts of the weld are molten at the same time and also cool at uniform rate. Hence, minimizes the residual stresses. And hence ideally suited for assemblies. The applications involves used in welding rails, heavy machine frames, locomotive frames, ship structures, etc. The next one is the gas welding. In gas welding, either oxygen, hydrogen, or oxygen, acetylene, is used to burn in burner used to create torch and with a pointed flame. We want to pinpoint it so that the heat is kind of is in compact form. This flame is directed upon the surfaces to be joined. The intense heat of the flame would melt the adjoining parts and simultaneously the welding rod to supply the molten metal to the joint. Further, a flux is used to remove the slag and in this process the controller or the welder has control over heating and cooling rates due to slow rate of heating from flame. So applications is to weld. The next one is the electric arc welding. In the electric arc welding, the heat required for the fusion is generated by the electric arc between the parts to be joined, and an electrode. This electrode can be made of filler material, and the filler gets consumed as the welding progresses. Electrodes and other kind of things. So this application is mostly popular in this machine building, industries, and structural work. Now the second part, which is where you need second group, which consists of application of heat plus pressure, is classified into two categories. The first one is a forge welding, and other one is electric resistance welding. In the forge welding, the parts are heated, the joining parts are heated to reach plastic stage, and the joint is prepared by impact by using hammer, by striking with hammer. Or a press can also be used. Applications would be like fabrication of wrought iron pipes. Otherwise, this technique is mostly obsolete now. The next one is electric resistance welding. In this, the joining parts to be connected are clamped and a high amperage electric current is passed from one part to another, and the resistance of the metallic parts to the electric current generates heat. This heat is used in melting the joining parts. So there are several things that comes under thing is spot welding. Spin applications are spot welding, seam welding, and others. And which is generally used in automobile industries. Now these are the lot of literature that we have studied. Now we'll talk about different types of joints, and once we study about different types of joints, we'll talk about the strength of those kind of joints. First joint is a butt joint. A butt joint can be defined as a joint between two components lying approximately in the same plane. We'll show you some types of butt joint here. So these are the different types of butt joint. The first one is square butt joint. This is V butt joint, U butt joint, double butt joint, and V butt joint with the backing strip. So let us know when these different types of things are used in the different scenarios. The first thing, square butt joint. So in this, there is no preparation of the edges. As you see, this edge is rectangular, this edge is rectangular. So no preparation of the edges. And this is preferred when the plate thickness is less than 5 mm. That is very thin sections. This is the plate thickness. And when the plate thickness is less than 5 mm, so these things are used, and the way it appears, you can see, is in the squarish manner. So that's the reason these are called as plate thick or square butt joint. Whereas when the plate thickness the second one is V butt joint. Plate thickness is between 5 to 20 mm or typically 5 to 25 mm. And this is the edge. It has been beveled. So next, edges are beveled before welding operation, and two edges V shape. So this and this forms a V shape, and since it is being done from one side, the welding is done from the top side, it is called single welded V joint. Now the other one is U joint. When plate thickness is more than 20 mm, these are used, and the edges are again beveled or machined to form a U shape, and the joint is again done from only the top side of it, from this side, so it is called single welded U butt joint. The fourth one is when plate thickness, it is called double V. So when plate thickness is greater than 30 mm, these are used. In this, both edges are again prepared, and they are kind of beveled into a double V. That is, top one V like this, bottom one V like this. If you look at here, you can see this is V. From the bottom side it is into this thing. Similarly both the plates, and the welding is done not only from the upper part but also the called joint is welded from both sides and hence called double welded. V butt joint. And the fifth one, E, is, you can see this one, there is a backing plate at the bottom and you have a beveled V shape on the things, and you again weld it from the one side. And this backing plate is provided so that this molten fluid doesn't escape from the another side. So it is a one-sided weld V joint, or one side welded V joint with a backing plate. Backing strip or a plate to avoid the leakage of molten metal from other side. And this backing plate is of two types. So one is permanent steel backing plate or removable copper backing. These are the types of butt joint we generally have. The next one is fillet joint. A fillet joint, also called as lap joint. It is a joint between two overlapping plates or components. Further, a fillet weld consists of an approximately triangular cross section joining two surfaces at right angles to each other. So further, this fillet joint is classified into two things. One is transverse fillet joint and another is a parallel fillet joint. So we will show you a picture. So as you have seen here, this is one and this is another. They are overlapping at each other, and you can see a small fillet cross section which is approximately like a triangular, a black triangle here. That is the fillet cross section, and that is in the transverse case is running perpendicular to the application of force. This is the length of the weld, which is perpendicular to the direction of the force. And in this case, there are two such kind of fillets, one attaching the top plate and one from the bottom plate. So this is called double transverse fillet things. Whereas in this case, and the bottom plate, the top plate is shorter of width, are attached along this length of the overlap, which is here. Whereas the earlier case, it was in transverse, it was attached at this place and this place. Now it is attached in the thing. So this is the parallel fillet weld, or also known as longitudinal fillet weld. Since you have two things, they are called as double parallel fillet welds. So let us take few definitions. Transverse fillet weld is defined as a fillet weld in transverse of the direction just a minute. A fillet weld is transverse is transverse if the direction of the weld is perpendicular to the direction of the force acting on the joint. Similarly, parallel fillet weld is a fillet weld is parallel or longitudinal if the direction of weld is parallel to the direction of the force acting on the joint. So this is the parallel weld and this is the transverse weld. Further, the cross section there are two types of cross sections. One is triangular and another is this triangular is an isosceles triangle and the other one is convex shape. So that would look something like so the normal or triangular is this kind of a thing and the convex shape would be rounded in this given manner. What happens is because of this roundness there will be a lot of stress concentration or the residual stress concentration at this place. So most of the time this is preferred cross section compared to the convex cross sections. So with this, what we'll do is we will stop here today, and in the tomorrow's class we will talk about the strength of the parallel fillet welds, the strength of the transverse fillet weld, and when you have welds subjected to torsion, welds subjected to bending, and there are other cases like you have eccentricity of a weld joint within the plane. Are those cases, and if possible we'll also talk about fatigue failure or the fatigue strength of the welded joint are the things that needs to be covered further in the welded joints, which will be taking up tomorrow. So once we have those mind, we'll also solve a couple of problems tomorrow, and using those problems we'll understand how one can design the welded joints for the machine components.